Good morning, everyone. In the last class, we have discussed about the pendulum governor and the gravity-loaded governor. For example, Watt's governor, Porter governor, and the Porter governor. Today, we are going to discuss about the spring-controlled governor or governor. In the spring-controlled governor, it consists of two bell crank lever pivoted at the point 00 to the frame as shown in the figure, and the frame is attached to the governor spindle and they rotate with it. Each lever carries a ball at the end of the vertical arm OB and a roller at the end of horizontal arm OR as shown in the figure 1. A helical compressive spring provides equal downward forces on the two rollers through a collar on the sleeve is also given in the figure, and the helical compressive spring serves the purpose like deadweight load. The spring forces may be adjusted by screwing a nut up and down on the sleeve, and the nut is also presented in the figure 1. Then the line diagram of the Hartnell governor is shown in figure 2, and here small m is the mass of each ball and capital M is the mass of sleeve. R1 and R2 are the radius of governor at the minimum and maximum positions. Omega 1 and omega 2 are the angular speeds of governor at the minimum and maximum radius of governor, and the capital S1 and capital S2 is the spring force exerted on the sleeve at the minimum and maximum angular speed of governor. And the central figure force Fc1 and Fc2 are the forces at the minimum and maximum angular speed of the governor. The small s is the stiffness of spring or the force required to compress the helical spring by 1 mm. X is the length of vertical or the ball arm of lever in meter, and Y is the length of horizontal or the sleeve arm of lever in meter, and R is the radius of fulcrum O from the governor axis or the radius of rotation when governor is in the mid position. For the minimum position, when the radius of rotation changes from mid position R to the minimum position R1 as shown in figure 3a, the compression of the spring or lift of sleeve is H1 is given by the equation 1, that is H1 upon Y is equal to A1 upon X is equal to R minus R1 upon X. And then for the maximum position of governor, when the radius of rotation changes from mid position R to the maximum position R2 as shown in figure 3b, then the compression of the spring or lift of sleeve H2 is given by the equation 2, and that is H2 upon Y is equal to A2 upon X is equal to R2 minus R1 upon X. Adding the equation 1 and 2, we get the equation 3, and that is H1 plus S2 upon Y is equal to R2 minus R1 upon X. So the total height of the governor H is equal to R2 minus R1 into Y by X is represented by the equation 3. Then for the force analysis, taking the moment about the point O, we get the equation 4, and that is the Centrifugal force Fc1 into x1 is equal to weight of the sleeve capital M into G plus spring force capital S1 divided by 2 multiplied by the horizontal distance y1 plus weight of the ball mg into a1. So the fourth load weight of the sleeve plus the spring force at the minimum position mg plus s1 is equal to 2 upon y1 multiplied by centrifugal force fc1 into x1 minus small mg into a1 is given by the equation 4. Similarly, for the maximum position of the governor, the weight of the sleeve capital mg plus s2 is equal to 2 upon y2 into fc2 into x2 minus small mg into a2 is given by the equation 5, and subtracting the equation 4 from the equation 5 we get the equation 6. In the working range of governor, theta is usually small, so the obliquity effect of the arms of the bell crank lever may be neglected, and that condition the vertical distance x1 is equal to x2 is equal to x and the horizontal distance y1 is equal to y2 is equal to y, and in that condition a1 is equal to a2 is equal to 0. Then we get the 6, and that is S2 minus S1 is equal to twice into FC2 minus FC1 multiplied by X upon Y. We already know the difference of the spring force S2 minus S1 is equal to height of the governor into the spring stiffness, means S2 minus S1 is equal to H into H. So height of the governor H is equal to, we know, R2 minus R1 into Y upon X. By substituting the value height of the governor and the stiffness of the spring into the equation 6, we get the equation 7, that is spring stiffness S is equal to S2 minus S1 upon H, or we can say S2 minus S1 divided by R2 minus R1 into X upon Y. Substituting equation 7 into equation 6, we get, substituting equation 6 into equation 7, we get S is equal to S2 minus S1 upon H is equal to twice of FC2 minus FC1 divided by R2 minus R1 into X upon Y whole square. When the friction force is also taken count, then the weight of sleeve mg may be replaced by capital Mg plus minus F. Then the problem on the Hartnell governor. A Hartnell governor having a central sleeve spring or two right angle bell crank lever move between 290 rpm and 310 rpm for a sleeve lift of 15 mm. The sleeve arms and the ball arms are 80 mm and 120 mm respectively. The sleeves are pivoted at 120 mm from the governor axis and the mass of each ball is 2.5 kg. The ball arms are parallel to governor axis at the lowest equilibrium speed. Then determine the load on the spring at the lowest and highest equilibrium speed and the stiffness of the spring. Here mass of the each ball is 2.5 kg, so small m is equal to 2.5 kg. Mid radius of the governor R is equal to 120 mm. Height of the governor S is equal to 15 mm. The horizontal distance Y is equal to 80 mm, and then vertical distance X is equal to 120 mm. So for the minimum speed N1 is equal to 2 rpm. So the angular velocity, minimum angular velocity omega 1 is equal to 2 pi n by 60, and that is 30.4 radian per second. And the maximum angular velocity, here the maximum speed is 310 rpm. So omega 2 is equal to 2 pi into 310 divided by 60, that is 32.5 radian per second. The lowest position the governor is shown in the figure, and the highest position shown in the figure 7. Load on the spring at the lowest and highest equilibrium speeds. S is the spring load at the lowest equilibrium speed, and S2 is the spring load at the highest equilibrium speed. Then the centrifugal force at the minimum speed, that is Fc1, that is m1 omega 1 square upon r1, and that is 217 Newton. And the position of the ball arm and sleeve arm at the highest equilibrium speed is shown in figure 7. And here small h is equal to r2 minus r1 divided by y upon x. R1 is equal to R is equal to 120 mm. So R2 is equal to R1 plus H into X upon Y, and that is 142.5 mm. Then the centrifugal force at the maximum speed, that is Fc2 is equal to m2 omega 2 square into R2, that is 376 Newton. By neglecting the obliquity effect of the arms and the moment due to weight of the balls, we have the lowest position, and that is capital M into G plus S1 is equal to twice of centrifugal force at the minimum position Fc1 into X upon Y. When the mass on the sleeve is 0, then the spring force S1 is 831 Newton, and the maximum speed control force at the maximum angular velocity S2 is 1128 Newton. Then the stiffness of spring small s is equal to S2 minus S1 upon the height of the governor, that is 19.8 Newton per mm. Thank you. In the next class, we will discuss about the stability of the governor and the effort and the power of the governor.